Okay, good afternoon again. Welcome back again. Here's what I want to do. We got a little bit delayed this morning because the notebooks didn't work as expected. I want to do one demo of the Jacobi C++ example that I had made. As we discussed during lunch, it's nothing to do with Jacobi anymore, but the name has remained. So this is a notebook I have in the directory examples Jacobi C++. And the very first cell I have, all of those cells here are marked with an exclamation point at the beginning, which means that we actually execute that on the outside of the cell itself. So the cleanup is just that. First of all, because it's C++, I have to compile the code. So cmake -s directory build, and here I'm compiling standalone actually. Yeah, so there's no Ascent, there's no Catalyst. And when you inspect the source code, you actually see the difference of all of them, all of those different versions. Then I compile. This was the configuration phase. And here is the submission of the job. I submitted job S1 on 4 tasks. The executable, the mesh type is uniform, and I give it a resolution of 64 so that it finishes very quickly. And indeed, it's already finished after 10,000 iterations. And then I plot the solution. And as you expect from a heat diffusion problem where we initialized the grid here, it's a 2D grid, we initialized here with a linear increase and decrease of temperature, then temperature goes on slowly into the available space. So that's the standalone version, and I can just stop that kernel and discard it. Then I want to run the same notebook but with Ascent. So I start by cleaning up everything. I make a new directory with the Ascent flag, -d in-situ equals Ascent. Then this actually has a lot of stuff and some warnings, but it goes through. I need to build it. The CUDA compiler was detected here. Everything is pretty cool. I'm making it, and there is now the submission of my job. So I start by making up a directory under the Scratch file system, which I will call Ascent test, and then I submit my batch job, run ascent.sh, and we can actually look at this run ascent.sh. That's the job. One node, 4 tasks. I load Ascent. I make the directory. I copy. There we go. I copy the Ascent actions.yaml and the plot actions.yaml to my current working directory. This is done to override the Ascent actions I have embedded into the code. Remember, I told you to do it this morning. So, which means we don't have to recompile the code here. We can specify any visualizations algorithm we want, and we're going to look at the details of those. Then I push to my runtime directory, NIS1 my Jacobi solver. Here I've changed the resolution to 128, that's fine. I pop and then I copy my solutions files to dot, which is the directory right over here. So let's look at those two files, the ascent actions and the plot actions. And then things should be pretty clear. Ascent action, there we go. I've added a trigger, and my trigger is pretty simple. I say when the condition iteration number is a factor of 1000, then execute the plot actions. Let's look at the details into that plot actions, which is over here. And that's my plot. It says to add a particular scene with the pseudo coloring of temperature. And if you follow me, I have one scene and then one extract action, and that extract action uses relay and the protocol blueprint mesh HDF5 to save a file which visit can load. So every 1000 not meters, but iteration steps, I will execute those two things. Any questions? No? All right, so I've run my job. Let's see, where am I? Over here, the job has finished. I load matplotlib. First of all, to look at the final solution. Okay, looks good. And the piece about visit is not in that demo. It must be in another demo. Okay, fine. There. I'm done with this piece. So this piece belonged to the morning session. But we're going to do the same again with Catalyst this afternoon. So if you have any questions here, but the principle will be the same. We're going to compile the code with a different option. Instead of using the in-situ flag over here, instead of using the keyword ascent, we'll use the keyword catalyst. All right. Okay, before talking about ParaView Catalyst, I need to talk about ParaView. Now, ParaView is a big project. It's over 20 years old, 1.6 million lines of code, interface to C++, Java, script, Java, Python, a number of classes which is in the hundreds. It's used worldwide. I myself, I have given tutorials of ParaView in Australia, in Sweden, in Norway, in Canada, in America, in France, in Switzerland too. So it's used a lot, which means I cannot teach you about ParaView in this afternoon. We don't have time. I've dedicated tutorials to that. If your organization is interested, perhaps I could come to your organization and give a tutorial. So very briefly, in 5 lines, 5 links, I have the presentation about ParaView. The introduction, ParaView, and I will read from the slide. It's open source, it's multi-platform, so it runs even under Windows 10. Multi-platform, open source, it enables multiple forms of parallelism, CUDA, VTK-M, TBB, OpenMP, all those different flavors you can compile into your application. Okay? It supports hundreds of different file formats. So, again, about file formats, before you invent your own, first double check what the standard visualization applications use. Maybe there's a format that you can write that is already supported. So that's for the introduction. And then you have the pointers, so you can look at those with more time when you go back to your own institution. In terms of architecture, if you download ParaView, install it on your laptop, you'll have together what is called the client, the data server, and the render server, all packed into the same box, into the same executable. That's a standalone application which runs with OpenGL, and it will do all of this, reading the data, doing the visualizations algorithm, rendering. That would be the simplest case. Furthermore, the data and rendering server can actually run in parallel, so you can have multiple of those, and you connect to a client. You can do that on your own laptop, for example, or you can connect your laptop to a supercomputer. So this part, the parallel part, will run on the supercomputer and will send images in most cases, or if the data is very small, it can also send the data to your client. And on PITSDANE, for example, the data server and the render server are together. What does it mean? It means they're together. What else can I do? The last option, which I have never actually operated, and I think it's seldom used, is where we have a separate compute resource to do the data serving and a second resource in parallel to do the render server. But that's a bit more complicated. So basically what you find at supercomputing centers is this configuration where you have the parallel data and render server compiled. The difficulty on a supercomputer is you don't have X windows. This is easily handled by ParaView. We use EGL, which is the embedded OpenGL working with a frame buffer that does not have to be visible. So that's for the architecture. To verify that your application runs in parallel, you can do a simple sphere like this. If you use 4 processors, you get 4 different colors. It means that you are effectively running in parallel. More to this later on. When I talked about parallel data server, I also said parallel rendering. How does parallel rendering works? It works exactly like this. Each compute task has a subpart of the data and of the geometry. It makes an image of the subpart, here 4 of them, and then there's a stage called the image compositing, which brings back together all those contributions with the correct depth and opacity information, such that the final image is what you expect, and that final image is sent to the client. So from the client's point of view, it's transparent. You can have 4 compute nodes, or you can have here, I guess it's still 4 here, yeah. Or you can have as many as you want. The final composited image is one only and is sent to the client. And this this composition is done in a binary tree fashion like this. So the first two compute nodes here would compose their image together. The next two would compose it together. Then they merge. So it's a tree of size n if we have 2 to the n tasks. Okay? And that works transparently. So we've done with this. This is an accelerated ParaView tutorial. Then we have ParaView and Python. We have another pointer for you to read when you go back to Zurich tonight on the train. Homework. Hello. Doesn't work anymore. I'm clicking, but the link doesn't do it. In a few words, ParaView is an interactive application, first of all. So you load your data, and then you spend time trying different algorithms, different parameters, different view, etc. And then you want to save not only an image, but you want to actually save the program that makes that image. And that program is made in Python. And ParaView will save it for you. And that's the great thing about it. And this is the part that interests us, because for in-situ visualization, we're going to use a Python script which ParaView has saved for us. Don't know why my link doesn't work anymore. Then there is one more link for you to look at, PVPython and PVBatch. PVBatch is the Python-based parallel execution program for the cluster in batch mode. So there you don't have a client. This is what we run on PitchDaint when we do, for example, a movie animation. To do a movie, I simply need to reload the same visualization program for multiple steps, and I don't need to be connected to my client. So PVBatch and PVPython are the two executables that will allow that. It's pretty strange that those links didn't work. Okay, so let me give you the super fast demonstration of ParaView. Here's ParaView loaded here on my screen. I need to make it fit. There we go. ParaView comes up with an empty screen. I'm going to make up some data with the fast uniform grid. Apply. Here, I have a volume of data which I show in outline mode. And here you can see that I have multiple choices. I can do the pseudo color plot that we've shown earlier this morning called surface. I can do volume, I can do points. If I do points, point Gaussians, this is what I have, etc. You got it. I can put a color onto this, which is selected over here, and that would be this numerical field called distance square. It's the distance from the center of the volume, and that's fine. Now what do I do with this? I can do multiple things. I could do, for example, an ISO contour of variable distance square at value at threshold 100, and this is what I get. If I put back my box in outline mode here, you can see it very well. I have the volume, I have an isosurface, but I want to see inside that I want to clip it. I decide to clip it, so I do this and this, and I apply, and I hide, and now I have, sorry, one more. I'll change the input. I'll use contour, OK. No, I didn't want to slice. Sorry, I wanted to clip. No, delete, clip, apply. There we go. So I have my iso surface clipped halfway. Good. The data is not very interesting, I'm sorry, but now I want to save this as a Python script. Look, this is pretty easy. I'm going to say save state. I'm going to give it a Python script, a Python file name, foo.py. I'll say OK, and then I'll quit, or else I'll do reset session. Yes. There. I have an empty plate here. I start ParaView. I say load, no, not load state actually, because this is a Python script, run script, foo.py, OK. And I'm exactly where I started. So that's how easy it is. Now suppose I want to do this in situ. I will use that Python script and I will feed that to Catalyst, and Catalyst will execute this on my grid. So the big box here is my computational grid. I know how to describe this computational grid with Conduit. I'm going to pass a Conduit node to Catalyst. Catalyst will execute this Python script. There's a little bit more to it, but we will come. So keep this mental model in place. By the way, this Python script is independent of the number of parallel tasks you are using. So you could read this small resolution cube on my laptop, move the Python script to the supercomputer, and read a big resolution volume in parallel, and the same image will come out. So that's very, very nice, very powerful. Okay. At lunchtime, I told you Catalyst version 1 was actually very popular and has been used in several large simulation codes in the past. Catalyst earlier, so before version 5.9, was a VTK-based API, which means to write the data adapter, you had to know the internals of VTK, and it's pretty complicated. Furthermore, you have to know how efficiently to do it efficiently, map your data to the VTK object. So this was not easy. I would say it was reserved for experts, not so much for a simulation code developer like you with a hobby for visualization. You had to be a developer in VTK to do this. So this is an exercise that you would do putting two persons together, an expert like me knowing VTK, and then the code writer knowing the internals of his simulation data. All of this, forget about it. Now there's Conduit since version 5.9. Catalyst is actually a separate product, source code from ParaView now. And writing an adapter requires a discrete knowledge of Conduit. This is what we've done this morning. We've learned in half an hour all we needed to know about Conduit to describe our data. Catalyst is a lightweight API which you compile in 20 seconds on my laptop. It takes about an hour to compile ParaView. So that gives you the difference in scale. Catalyst is a lightweight API which you link against with a stub implementation, and at runtime you say, I want to use the ParaView implementation of Catalyst. So that's the key to it. There's a nice blog article here which is linked into the presentation. You can look further. So ParaView Catalyst is an implementation of the Catalyst API. And it's the only one, as far as I know. No, actually, what I will present at the end, this is actually a Catalyst implementation now. So there is more. ParaView Catalyst supports a subset. I don't know exactly what parts are missing at the moment, but it continues to grow, so this perhaps is not a fair statement of the mesh blueprint. The mesh blueprint, we've seen that this morning. It's this convention of usage, which means that the effort that you put in this morning to encode your data for Ascent, that same source code description can be used for Catalyst. It uses the blueprint. Sorry. I've got a couple more pointers here about ParaView Catalyst itself, and then because ParaView Catalyst also uses Conduit for its API, we need a blueprint. This way we are sure to speak the same language. So a blueprint for Catalyst is just like the blueprint for meshes. It has a protocol to follow. We need an initialize function, an execute function, a finalize function. And for example, in the initialize function, we have a special keyword called Catalyst script, and then a file name. This will be the Python script which ParaView just created for me. Okay? Are you putting the pieces together? This is why we need a discrete knowledge of the ParaView Python syntax. And if we have that, it takes a few, really 1–2% of changing things, cleaning up the ParaView Python script to fit it to the Catalyst script. We will see the example of that. So there's a few more details, but the idea is to remember an initialize and execute a finalized function is all we need to care about. So I've said that we have inherited the description of the Conduit mesh this morning for your simulation data. We're done. How do we compile the whole thing? How do we specify the visualization tasks? We need two things. One of them are the so-called data extractors. The other one is the image extractors. So those extractors can execute at a given frequency given temporal frequency. So here, for each one of those, I can say, every 100 iterations, please execute, or every 50 iterations, whatever. We can mix and match. Using the extractors, you don't need any special code, really, in the majority of cases. The extractors will save images and data to disk. So what are those objects? How do we create them? The answer is back to my ParaView session here. There was one little piece missing here. I'd say, okay, I want to save images. So let's create an image extractor. If you follow my mouse cursor, I go to the extractor menu and I say images. I want to save in PNG. I have a trigger over here, the time step. I have a frequency. I can say every 100 time steps. There we go. I have a file name over here, which is the render view, which can be changed here. The file name encodes the time step, iteration number, and then a parameter based on the camera, because we have an option also to make multiple views with a given camera. I don't think, I haven't prepared, I don't have time to present this, but this is in there. There, I apply this. Why did my thing disappear? That's a mystery, but it's not so important. Actually, it is important. There we go. Now, this nice ISO contour, I would also like to save this to disk because it represents maybe my turbulence, maybe it's a lambda 2. People doing fluid dynamics, they're used to that, looking at those lambda 2, ISO surfaces of lambda 2. I want to save that to disk, so I'm going to select the contour object. It's already selected here. See, when I click on it, it gets selected. And I'm going to say extractor data VTP file format. I will enable it. My trigger will be the time step. And I'm going to say every 500 time step, I want to save my data. And the data, the file name will be called contour1 timestep.pvtp. PVTP is the parallel version of the VTP file format, which means that this can run in parallel and it will save a distributed file representation. I say apply and I'm done with it. Here nothing really happens, but the trick is if I now save my state to the same Python code, I want foo, pi, OK, yes. First thing, extract output directory. This name will be the directory name where in situ all the things will get saved. So you can modify that too if you want. There. I will disconnect from everything, clean up, restart, reload my state. And I'm back. Everything is cool. By the way, I have exactly the right orientation of my camera. Everything gets saved. Here nothing happens because I'm not in situ. This is ParaView. But that Python script is what I will feed to Catalyst. Let's exit. I want to go back to my terminal. Is that too small? Yes, probably. How do I change the font size? Let's make it big so that you can see that on the screen. And I want to take a few minutes to look at the details. Here, first one, create a view. So you can update the view size to be exactly what will fit in situ. Here's the camera position. We can always change that to something that we like. That's for our first view. We have a second view. Here I have the name of the data producer. So I read, instead of reading data from disk, here I just generated a computational domain online. But that's what it's called. But this is very important, this name. Actually, this is the instance name. Then I do my ISO contour algorithm, contour, and the input to contour is, of course, the fast uniform grid 1. So this object is the original data. It serves as input to the contour. Fine. Then there's the clip that we did, which clips the contour, and we're done with this. And all of this can be simplified. I want to go to the end. And there is what we need for in situ extractors. The first create extractor for the type VTP, the proxy, it's called proxy in this case, is the ISO contour. I want to save the ISO contour based on the trigger time step every 500 time steps. And this is the file name. Okay, pretty easy. Same thing for the image. We create an extractor of type PNG. The proxy is the view. The time step trigger is 100 images. And here's the file name. And we're at the end of our script. Actually, at the very end there's a special code. If name is main, save the extract. This means we are in an in situ situation. Otherwise, when I use the ParaView client, I reload the Python script and nothing happens. So there. The key to using Catalyst is having those extractors defined based on a given frequency. You can change all those other parameters. And then up above, you have your, there's a little bit of details, but you have your visualization pipeline, the data producer, the multiple visualization filters. One becomes the input to the next, etc., until you make an image. So you can prepare a Python script like this at low resolution with a sample of your data. And then when you run it at high resolution, nothing has changed. If you run it in parallel, there's nothing in that Python script that says anything about parallelism, MPI task, and all this. If, for example, instead of contour, you use the TBB accelerated isocontour filter, also there, it will just take whatever hardware it finds to execute. So we're done with this. Any question? Good. Okay, we've done this. Python scripts are written by the application, which you develop interactively, then you fine-tune, and then you send to the Catalyst runtime. Since ParaView provides, out of the box, MPI-enabled parallelism, TBB multithreading, CUDA-enabled filters, all of those will become active when you do in-situ. Yes, the same Python script is interchangeable between PV batch, the batch mode-oriented execution of ParaView, or in-situ. Jean-Guillaume, you have a question?
I'm trying to understand the difference between Catalyst and Ascent. If I understand, an easy way to differentiate is to say that if you like Visit, you should use Ascent. If you like ParaView, you should use Catalyst, or it's more than that?
It's a bit more complicated. First of all, the difference. So, the common denominator between Ascent and Catalyst is the conduit node description of your computational domain. That remains the same. The differences between the two is that the Ascent visualization pipeline is defined using Conduit, using the Conduit syntax. Whereas the visualization pipeline for Catalyst is defined using the Python syntax of ParaView. Now, which one do you prefer? I've used both of those systems for, you could say 20 years. Like everything in life, for a little bit of time you like rock and roll, then you like reggae, then you like classical music, then, right, you have different phases. So I've had my phases. I've had moments in life where I preferred Visit, moments in life where I preferred ParaView. At the end of the day, each one will, there's a large common base of filters which you can find in both of them, and there are some specific filters, algorithms, which you will find in one only and not on the other application. So that might be the deciding factor for choosing one or the other. Then there's also the level of API integration, which at the moment is important. Ascent supports C++, C++, Fortran, and Python. At the moment, Catalyst is only available in C++, but just yesterday, the Python bindings and the Fortran bindings were merged into the code. So next time I teach this tutorial, I will have really the whole thing. Okay, so that's also important, I think, the language that is available for our runtime. So let's look now at some important differences between the Python script usable by the ParaView application and the Python script usable by the In-situ Catalyst wrapping. This would be a very simplified version of the ParaView Python script. I open some data file with a particular registration name called grid. This registration name is the name that you see in the graphical user interface of ParaView. This instead is the name of the proxy. And here I've read one of the time steps of the Lulish output. Then I create a view. I show this view, which makes this show command is the command that says make an image. And I color this by the velocity vector. And I render. This would be used in ParaView. In situ, the two differences are this. Grid, basically you remove the line of code that says read data from disk, because there's no more disk. And you replace this one line by this line, trivial producer. Registration name is grid. So the name here is the same, and that name is the name that you will find in the Catalyst blueprint convention. That's all there is to it. So if you match that name with what you've put in Catalyst, then you're good. And when ParaView executes this, it will say, oh, I recognize this. This comes from the Conduit data channel. This stays exactly the same. This is the same. This is the same. And we've seen how to create an extractor to save my grid at a given frequency into a particular file name. I think those are the two differences. So it's pretty simple. Replace, so this could be in your original data, you could have Fluent data, TechPlot data, Insight data, whatever data, HDF5, NetCDF, anything. You benchmark your ParaView session with this, and the name will change here based on the reader that is being used. When you change to go to In-situ, you change this by a trivial producer. This is a special macro that knows what to do. And then you add your extractor. The protocol, we've seen that already briefly. There is an initialize, execute, and finalize command that need to be available. There it is. So with the blueprint of Catalyst, we've looked earlier at the documentation. There is the keyword Catalyst, then script, and then you can have several of them, but you give it the file name, which I called foo.py on my computer here. You set up the cycle and the time, the grid type, etc., and your data, and then you're good to go. So back to the SPH code earlier, this astrophysics simulation code, which I've mentioned earlier this morning. The implementation, well, with Ascent, I had 150 lines. Here I have 144. No much different, okay? enabling in situ is completely optional. This is the way I do it, at least for demonstration purposes. Here's my main code, an MPI init, whatever. And then for a set of iterations, run my solver, iterate. If you do Catalyst, you include your adapter, you do your initialize adapter, and you pass it argc and argv, because presumably the name of your Python script, you put that on the command line. And at each iteration, you execute the adapter. But this actually might be a no-op. If your extractor says to only do the operation every 100 step, then it doesn't cost it. It's a function called to null and it returns back. And then when it hits the correct time step, then it does the real work. At the end of your at the end of your iteration, you finalize and you quit. I've talked about operations control this morning, thresholding, triggering. Here's an example of thresholding with the ParaView code. This is back to my animation of with SPH exa. I want to look at the point data, the density field. I want to look at the maximum value of my range. So this is 1. If you do get range, you get minimum and maximum. Maximum is the second value. If that maximum is greater than the threshold, I extract the particles where the density is greater than threshold. Otherwise, I use all particles. This would be ParaView Python code. So this is where you need to have a discrete knowledge of the ParaView Python syntax, which, let me think, is perhaps a little bit more complicated than programming the Ascent visualization pipeline, but not much difference. Look, for example, here at the syntax. My reader object has a dictionary called point data for each of the variable names. So you can get access to each of those variable data arrays and information pretty simply with this type of syntax. And then doing the extracting here would be a selection filter, which you can prototype with ParaView itself. Okay, so operations control, ParaView, we've mentioned the client-server mode. It will do everything in parallel, the I/O, the filtering, the image composition, and the image delivery. So image delivery means that the big data, your computational data remains on the server side, and it's only the image that gets moved into the client. If you look at a small image size, 1024 RGB, then that's very few megabytes moving along. This I have a demonstration of using ParaView live to connect in situ. Unfortunately, I forgot to replay it. I have the video of it. If I find it during the break, I will show it to you. So a number of examples, demonstrations I have prepared. One of them is, again, the Lulish code coming from the Proxy Apps consortium. There's one version of it, VTK based, so that's Catalyst version 1. You could look at it for your curiosity. Or there is a Conduit based implementation of it, which Utkarsh, when he was at Kitware, contributed. I've made my own example such that I could put both Ascent and Catalyst in the same code, and that's what we have on PitchDate. So to execute the code, you can also do that via a Jupyter notebook. And here I forgot to change the name, but this is called, because we're doing Catalyst, it's called Catalyst How to Compile in that directory. And then you can, yeah, this is the notebook right here. Again, I forgot to change the last name. I told you that I had an accident. I lost a number of data yesterday in my PowerPoint. Then I had to redo things. I had corrected those things. Never mind. So let's do the exercise. And then we'll look at the differences. Here's the ParaView pipeline for reading my data, creating a view, selecting the points where the density is greater than 1.4. This would be the ParaView syntax for it. Extracting that selection, coloring those data by the scalar field density, making an image with the extractor at a given frequency. This is with ParaView. On the right side, this is with Ascent. You create a pipeline with the threshold operator. Just because I wanted everything to fit on one screen, I didn't put it, but under the threshold, you have the parameter greater than 1.4. Then you add a scene, you plot with pseudo-color the output of the pipeline 1, and under renders, you create an image prefix, threshold image. I hope I use the same file name, yes, threshold. And in the Ascent options.yaml, you put your trigger to say, I want to trigger every 100 iterations. Otherwise, it's more or less the same things. All right, now is the time for you to do a little bit of work trying those demonstrations. So the first one I would try, I will do it here first, then you can try it later, is to run my Jupyter notebook, which has most likely expired. So I need to restart. Okay. It will be a few seconds. I'm going to, we looked at the Jacobi example. So the Jacobi C++ example, I will now compile it with ParaView Catalyst, and I will execute Catalyst on that data. Then I suggest for you to look at the Python examples. So there's a couple of them with different notebooks. And then I will, when I see the screen here, I will know where to point you to. So under project, In-situ visualization, examples, Jacobi C++. I'm there. with Catalyst, the notebook. There it is. So I do my cleanup. I configure my compilation, this time with the Catalyst keyword here for CMake. So it's found MPI, like everything is good, configuration is done. I will now compile it. And I will now submit it to the runtime thing. So I make a temporary directory under my Scratch partition called Catalyst Test Images. Why not? And then I do srun with 4 tasks. The mesh type is uniform. You're welcome to change that for your. And the difference is that I pass the name of a Catalyst Python code. I pipe this to dev null because this creates a lot of warnings. I wish, well, with the next version of ParaView Catalyst, those warnings will go away. So they clobber the screen, that's all they do. This is why I was not in favor of showing you those things. I use my matplotlib thing to look at the final solution, and lo and behold, thank God I have the same solution rendered both with Catalyst and Ascent. Now, I just wanted to point to, the Catalyst state. So this was the main difference in the way we executed the script. Let's look at the content of this script, Catalyst state. We're over here. Let's look at the details. I get the address of my Scratch directory on Pete's date. So there's an environment variable called Scratch. Then we've seen all of this before. Create a window of resolution 800 square with a given viewpoint, zoom, etc. I load the palette white. And here's the thing, trivial producer with the registration name grid. I show this in outline mode because I want the border of the grid, which I color with temperature. It's not so important here. Then I do the ISO contour lines with in this case, they're not ISO surfaces, they're ISO lines because we're in 2D. But the keyword is still called ISO surfaces. It's a range of 10, 11 numbers between 0 and 1 because the temperature is between 0 and 1. I want 0, 0.1, 0.2, etc. Here, just for illustration purposes, but that's not important otherwise, I use another filter called process ID scaler. This will color the ISO contour lines by the processor ID which did the work. I show this particular output with a line width of 2 because I want the lines to show up a little bit better, and that's it. I reset my camera, and we've seen that before. The create extractor, every 2000 time steps, I want an image called this view thing of resolution 800 square PNG every 10,000 steps, I want the output of the data set. And then here, we haven't seen those earlier, but they're actually saved for you by ParaView. The ParaView Catalyst options, the trigger time. If we want to enable Catalyst Live 0 or 1, if we want to enable a particular SSH channel to connect the client, we give it here. And then we give it the extract output directory, which is the same name I used earlier to make the directory. And I was convinced I had shown, I must have done it for another demo. I think I did yesterday for this demo. The catalyst. Okay, yeah. I did it for another demo. I could cut and paste. Let's try it. Cut this, run here. Okay. What I want to do here is actually look at those images. So I want to use the Ascent image sequence widget to look at my images. And I just have to change the file name because those images are, what are they called? They're in catalyst.state, so they're called catalyst state. They're called catalyst state, I'm not sure. Or they're called images. They're called, let's look again, catalyst/test. I'm surprised by the name, but okay, test. Thank you. Yes, now I remember it. With I'll get it. Okay, something works. What do I have here? I have the ISO lines of temperature, and if you can distinguish the colors here are different because they come from the 4 different MPI tasks which contributed to the in-situ visualization. There, so I'm done with the demo. Now it's your time to replicate some of that. You can try it with the Lulesh test demonstration. You can try that with the Jacobi Python where there is with Jacobi Python I did not make a catalyst interface because there was no Python binding yet for catalyst. So go to the Jacobi C++ and here there is a build catalyst with the instructions, but there is much better with catalyst, the notebook which we have here, which has all the instructions on building things. But then I think it's important to actually look how we implemented that. So actually, before I let you go for the exercise, let's look at the catalyst adapter. Here's the initialize function that we've seen is mandatory, is in the protocol. And here's the catalyst pipeline file name, which is the name of the Python script passed through the arguments to initialize catalyst. Let's look further down. No, I think I got confused here. The catalyst script is actually over here. Yeah, this is for the output. Sorry about that. The catalyst script is over here with the name passed on the command line. Something important. Also, this particular keyword, we need to tell Catalyst that the implementation we want to use is the ParaView provided implementation. And then there is an environment variable called Catalyst implementation path, which tells us where to find the library at runtime, and this is encoded into your environment for the demonstration. Now, let's look at the execute thing. We look right just at the beginning here. Look, this is exactly the Conduit code we created earlier. We have a mesh, we have a data, we have a type for the mesh, we have the coordinate set, etc., etc. And this is really just for demonstration purposes that I have put here all the 4 different mesh type, uniform, rectilinear, unstructured, and structured for this. Here you will recognize the temperature description. And then here I have one special one. I have a field. I have given it the name VTK ghost type. This is a reserved keyword in ParaView, which tells ParaView this field encodes whether the data is the data cell or the data point is a ghost cell or ghost point. So then ParaView can do some optimization on that. That's for the Catalyst adapter. If we looked at the Ascent adapter earlier, you will see the same code, basically. Here's for the rectilinear description. Catalyst state. We've seen, let me point you to one fundamental thing. The trivial producer here has this particular keyword, the name of the channel, grid, and this is what we find in the Catalyst adapter at the very top over here. We have the name of the channel is grid. If those two match, then you get connected. Okay, I will stop talking. You will do some exercise. I will be there present with you to answer questions. And let's look at the time, 3 o'clock. if we take the example of the Jacobi to the heat diffusion in 2D, if you were starting from scratch, here's what you would do. You would take ParaView on your desktop, launch it, create a 2D grid, put a scalar field in there, call it temperature, make it between 0 and 1, draw some ISO contour line, save the Python script, and this would be it. That Python script, if you give it the name temperature, it's already set. If you give it the correct range of scalar between 0 and 1, it's there, it's set. So then that Python script needs to be edited. You change the name of the producer, you call it trivial producer, with that grid keyword, which you inherit, and then you're done in practice. Right? Then you need to do the exercise a few times to understand. Jean-Guillaume, did you have a question? I need to come. A few minutes ago I said if you want to start from scratch, you generate a sample data set in ParaView. You give it a name, you call your scalar field temperature, and then you do the operation you want. So back to this heat diffusion example. If I wanted, for example, just as an exercise, threshold the data, cut off all the data that is greater than 0.5. Well, I start from this example. And of course, I can apply the threshold operator, just like this. I select my numerical field. I give it a set of parameters, and there is my selection. Okay? I can actually see which Python code ParaView executes using a particular feature which I want to demonstrate now. So I want to delete this. Okay, I start from here. If I go to the tools and I say start trace, show incremental trace, you will see what happens. When I threshold, it pops up on the screen right away the code that I'm interested for my visualization script. I'm interested in exactly the syntax of this. So it's called threshold. It has a particular input. The scalar is the name of the variable. And there's a lower threshold and an upper threshold. So those 4 lines actually are all I would need to copy and paste into my existing Python script, such that instead of showing the ISO line of temperature, I could show a threshold of data. Of course, you would have to change the variable name here and the threshold number over here, and then the input. But it's not so much difficult. Now, in practice here, I would go to distance square. I would say 0. I would say apply. And when I stop my trace, I have exactly what I need, which is over here. My lower threshold has been reset to 0, and the scalar to threshold is the correct, for this case, is the correct scalar field. So let me show it in reality. Control C. I will copy those 4 lines of code. I can exit ParaView. I don't need that. I will go to my catalyst state. Okay. Here I will insert my threshold command. The input is the reader. The scalar field is called temperature. Lower threshold 0.5, upper threshold is 1. Now instead of coloring the contour ISO line, I will color the threshold. So I take this and I replace it as input to the process ID scalar. If I save this and run my script again, yes, except that I'm running the wrong example. I want it to be in C++ over here. Okay, so this is correct, and I want it to run with Catalyst over here. I don't have to remake the compilation. I can just come over here to cell number 4 and execute that cell. And here's the result. I have now the temperature data thresholded below 0.5. And if I animate, I don't know if I have, yeah. Okay, those haven't been updated yet then. Okay, so I should wait. I should reload. Yeah, you see, it's still running, so it's overwriting the previous images. But we have the demonstration here, at least for the first 5 time steps, that instead of doing the ISO contour, I'm now doing the thresholding, and the color is just the color of the processor. Doesn't mean much over here, it's just for the demonstration. So we've seen that updating the Catalyst ParaView script is just this. Here I've replaced the contour by the threshold. And those 4 lines, I didn't have to look at the documentation. I just used ParaView to tell me exactly the syntax.